We're now going to start looking at situations where energy is not conserved. So that means between point A, B, and if you want to add a C, but we're really going to only look at points A and B now. You don't have the same amount of energy. So what's happening is that something known as work is being done on the object. So work is the force exerted on an object over a distance. It is literally the change in energy an object undergoes. So if you have a certain amount of energy at point A in the problem and work is then done to it, you will have a different amount of energy at point B. The units for work, because it is a change in energy, it's the same unit as energy, the joules, and the symbol for work is a capital W. Because energy can have a positive or negative change, your work can be positive or negative. So it'll be positive if the force causes the object to gain energy, and it will be negative if the force causes the object to lose energy. So it is possible to have negative work done. It just means that you have less energy than what you started with. Work's going to depend on three things. First is the amount of force acting on the object. Next is the total distance traveled from the starting point. And really, what I mean by that would be displacement. Because it's where it is versus, I spelled displacement wrong, didn't I? Let's just make that an E. It's where it ends up versus where it started. And then the angle between the force and direction traveled. And you'll see what I mean when we look at the example for what we are looking at with that angle. Really, you need to know two things. If the force is friction or anything acting opposite the direction of motion, the angle is always 180 degrees. So work is negative. And if the force is in the same direction of motion, the angle is always 0 degrees. So work is positive. So I'm going to give you the equations for work, and I'm not giving you the full equation because we're not going to worry about it. It does have an angle in it, and that's what I'm talking about with the 180 degrees and the 0 degrees. What you really care about is the fact that if you have friction or anything going opposite the way the object is moving, you make work negative. If you have anything pushing the object in the same direction that it's moving, you make work positive. And just think about it taking a step back more literally. What's happening? Is it getting faster? That means work has to be positive because it's gaining kinetic energy. Is it going higher? Work is positive. It's gaining gravitational potential energy. Is it getting slower? In that case, it's losing kinetic energy, so work would be negative. So we're going to use bar charts again and look at the problems and use those to help us figure out whether or not you have positive or negative work. So don't focus too much on the angle, just more in terms of it being 180 degrees or 0 degrees. Focus more on what way is that force acting relative to the way it's moving, and what is it literally doing to the object. Is it making it faster, slower, making it go higher or lower? That rhymed. So equation number 1, and like I said, there are two ways we can look at work. The first is work equals the force acting over a certain displacement. So it's the amount of force applied to an object over a certain distance, where W is work, F is force, and delta D would be your displacement. The units for work, I mentioned that those were joules. Hopefully you remember. So the unit for force is Newton. The unit for distance or displacement is meters. Hopefully you remember that a joule is a Newton times a meter. So that's where that unit comes from. Work is also the change in energy. So you can think of this as your energy at B minus your energy at A. So I'm going to circle this. Work is equal to your final energy at B minus the initial energy at A. And I will not do any problem where we look at more than 2 points. So we're always just going to be looking at the beginning and the end. And work is your change in energy, so it's your final minus your initial energy. So final energy and initial energy. Now, what equation do you use? It really depends on what you're given in the problem and then what it's asking you to solve for. So some problems you're not going to be able to use this because you don't have a force or a distance. It's not asking for it. So you're going to have to go right to this idea. Some problems, it's vice versa. You'll be given a force and a distance. You're going to have to use that. And you'll see as we look at the different problems how you know which one you use. It's just by reading the problem and picking out what it gives you. So let's do the example. Okay, so let's look at the example. A person pushes a 40 kilogram box a distance of 10 meters with 300 newtons of force. Just draw out what's going on here. Person is pushing directly on a box. It is moving. It's moving a distance of 10 meters. How much work is done by the contact force? So it tells you the person is applying 300 newtons of force. It also gives you the distance. So with the two equations for work, based on the fact that we are given a force and a distance, it's going to make sense to use the equation work equals F delta D. The box is moving to the right, the force is applied to the right, therefore the person is doing positive work on the box. So work would just equal 300 newtons times 10 meters. 300 times 10 is 3,000 Newton meters, once again also known as a joule. So the person does 3,000 joules of work on the box. But as the box is moving, we also have a 184 Newton friction force acting against it. So the box is moving to the right, but you have the friction force applied to the left. And I like to sometimes just kind of sketch this out. So the solid line is the force, and I should do this up here as well. The dotted line is the distance. Whenever they are in opposite directions, the work will be negative. And that's just because the friction is taking energy away from the box, whereas the person was putting energy into the box. So now my work would equal F delta D. Friction force points to the left, so this would be negative 184 newtons of friction times 10 meters, or negative 1840 joules. So positive work done by the person, negative work done by friction. Now we want to look at work done by the normal force and work done by the force of gravity. So on the box, there is an upwards normal force. And once again, the box is still moving to the right. Anytime you have a force applied perpendicular, so that means at a 90-degree angle relative to the way it is moving, work will always equal 0. So think of it this way. The force has to be applied parallel to the direction of motion in order for anything to be happening. It can also be applied at an angle that is not 90 degrees, but pushing upwards on the box is not doing anything in terms of the way that it's moving right or left. So anytime you have a perpendicular force, the work would equal 0 joules. And once again, by perpendicular, I mean the angle between the way the force is applied and the way the box is moving, which means that my force of gravity, which points down, is also perpendicular to the way the box is moving, So the work done by the force of gravity would also be 0 joules. The total amount of work done on the box would equal the work done by the contact force plus the work done by the frictional force. So we had 3,000 joules minus 1840 joules, which means the total amount of work done on that box is 1160 joules. You can think of this as the net work. I don't like to use network because it sounds too much like network, but this is the total amount of work adding the work done by every single force. We're not really going to be looking at problems that have more than 2 forces acting on them, so you're never going to have to do any kind of complicated addition or subtraction. It would usually be one force doing work. Sometimes, like in this case, you have a contact force being opposed by some kind of friction. The fact that you have a positive total amount of work means that in the end, even though friction takes some energy out of it, the object is still gaining energy. So now we want to look at this in respects to energy. So work is being the change in energy. It tells us the box was initially at rest and it wants to know how fast it's moving after traveling a distance of 10 meters. So remember that the other definition of work is your final energy at B minus your initial energy at A. We want to figure out how fast it's moving. So in this case, the box starts from rest, so it starts with nothing. Work is done, and this is positive work. We technically had that negative frictional force causing negative work, but overall it was the positive 1160 joules, and that's going to give us kinetic energy. So our old bar charts were separate A and B. This one, I'm connecting them with this work in the middle. If you overall have negative work, then the amount of bars here would just equal whatever you started with here minus your work. In this case, your positive work, whatever you add here to this, would be your total energy. The box starts at rest, so it starts with nothing. You do positive work, it now has kinetic energy. So we started with no work at A, which means the work is just going to equal the kinetic energy at point B. The equation for kinetic energy, work equals 1/2 mv squared. My total work was 1160 joules. That's equaling 1/2 of the mass, which was 40 kilograms, times v squared, and now we just solve for v. So 1160 joules equals 20 kilograms times v squared. 1160 divided by 20 is 58. This would be joules per kilogram, which is the same as meters per second squared. And then we take the square root of that, and we get 7.61, keeps on going, meters per second for the speed. So after it's been pushed 10 meters with that constant force and the friction opposing it, your speed is about equal to 7.6 meters per second. I realized this was a long example because I was trying to put as much as I could into one problem. Most of these problems are not this in-depth where you're solving for every little thing. I just wanted to be able to show you how multiple forces acting on an object are not necessarily all doing work, how the positive work is done by something in the same direction it's moving, negative is in the opposite direction, and then just the use of the 2 equations that we have for work. So we'll be doing a bunch of problems. Most of them I will give you a bar chart. We'll use the bar chart. We'll figure out what to set work equal to, whether it's force and displacement or whether it's EB minus EA. And then depending on what we have, we'll be able to solve.